Alright, so we've talked about simple harmonic motion. What we want to talk about today is not so simple harmonic motion. I guess it should be not so simple harmonic motion or damped harmonic motion. What I have up here is what's represented as an underdamped system, which means that there's a dampening on that system. It's bringing that object eventually to its equilibrium point. When we refer to this, there are three types of damped harmonic oscillators. There's an underdamped, an overdamped, and a critically damped. This one's an underdamped. Now, the really cool thing about a damped oscillator is that if you were to look at the amplitude of each cycle, okay, looking at the amplitude at each cycle, you find that those positional values look something that are, those positional values can be represented by this equation. Okay, is represented by this equation. So this means position equals the maximum position, which you can say is here, I guess, or which should be up here, times the exponent or the exponential of negative bt. B here is not actually a b, that's a beta. And it is called the dampening function or the dampening value. The beta is what's bringing the system to a stop. Okay, so as we look at this, we can say that this curve is represented by this equation. The total motion is actually represented by that equation times the simple harmonic motion. That's the total motion right there. But if in case you have to solve a problem where you're trying to find the dampening function, this value for beta, that you can draw this graph, and if you can fit the data in here, then you can solve for this. Or if you only know, in this case, 3 data points, you can say that this value is representing x max, this right here, and this value is representing x final, okay, and then this range from here to here, and I should have said this, this from here to here is t. So at that point you know this, and you know this. So all you have to do now is solve for beta. Okay? So that's an underdamped harmonic oscillator. That's what it looks like. If you wanted to look at an overdamped harmonic oscillator, it's kind of funny to call it an overdamped harmonic oscillator because it's not really all that harmonic. An overdamped harmonic oscillator will look something like this. Starting from a maximum point, it wants to follow that exact same curve, but it may do something like that. Okay? It's an overdamped system. Overdamped meaning that it doesn't go through a single cycle. It just collapses. As a matter of fact, this curve here that you're experiencing is nothing more than e to the, God dang it, x max e to the bt. The sine function is completely wiped out in this case. It's overdamped. It just goes. Now if you were to think about real life systems, and going back to my underdamped system, you can think of a real life system for an underdamped is anything. A pendulum, for example, is an underdamped system. It'll eventually, it goes like this, and eventually it'll come to a stop. Eventually. But it's traveled so many cycles before it stops. That's an underdamped system. The other way you can think about it is a mass on a spring. It goes up and down, and eventually it comes to a stop. That's underdamped. Now, critically damped, you can think of those as your swinging doors, like your patio doors, with the spring inside of there. You open it and you let go, and it just slowly literally closes. It doesn't oscillate. It doesn't go beyond the door frame and then back. It just goes to an end. Okay, so that's what an overdamped system looks like. And then like I said, an underdamped would be a pendulum that eventually comes to a stop. The last one is a critically damped system. Now, critically damped systems are great. Why they're called critically damped is that the system completes exactly one cycle before coming to an end. There's a function there, that dampening function is such that when the system, when you release it, it completes one cycle before, nope, it doesn't go back up, before coming to a stop. Okay, critically damped systems are great because those critically damped systems are the shortest time possible it takes to bring something to an end. If you have a door that swings and then comes to an end, or if you have a door that's allowed to swing all the way open and then swing back and comes to a stop, that's critically damped. It just goes through one cycle. Okay, and it's great because it's the shortest amount of time. If you need a system that needs to stop in the shortest amount of time, you want a critically damped system. So you can look for those systems in some cases. In some cases you can't. A critically damped won't work for a door because there's a frame in the way. It smacks that frame. Okay. Now, to solve for a critically damped system, we do it exactly like we do for an underdamped system, except for we need to use this data point. Okay, and this data point. This is going to be the absolute value of that x value. Okay, so you're just going to shift it over there, and then you can describe that motion by E x max. X is equal to x max e to the negative beta t. Okay, you know your time, you know your x max, you know this x. Solve. Or if you must, make this value 0 and see what it takes. The only problem with that is that this point is also 0. Well, no. There is no problem with that because you're following this trend, not that trend. So erase that. You can use the 0 point, right? Except for that would mean that time goes to infinity. Use that point. That point and that point. This is x. This is x max. You're following this curve right here. Okay, it's a critically damped, or that's a critically damped system. So that's the not so simple harmonic motion. All you really need to know is what makes a critically damped system critically damped, an underdamped system underdamped, overdamped, and be able to solve for this dampening function. Okay, cool.